Everyone, I am Nabila Tabassum. I am going to present my E275 Advanced Computer Architecture final project, which is implementation of Nios architecture, and the project is done under the supervision of my professor Dr. Chang Chu. Outline of my project is Introduction, Objective, Nios architecture overview, design hardware, design verification and analysis, future scopes and conclusion. The objective of my project is to design a 32-bit 5-stage pipeline processor based on Altera Newster architecture. The design is implemented in Verilog HDL, and for the simulation and compilation I have used Synopsys VCS tool, and for synthesis I have used the Design Vision tool of Synopsys. The Newst architecture describes an instruction set, not a particular hardware implementation. A functional unit can be implemented in hardware, emulated in software, or omitted entirely. The Newst instruction set is based on reduced instruction set computer architecture, which is RISC. Its arithmetic and logic operations are performed on operands in the general purpose registers. The processor uses separate instruction and data buses, which is often referred to as the Harvard architecture. The word length of the Neo 2 processor is 32 bits. This slide shows the data path of implemented design. There are 5 stages. The very first stage is the program counter block, which points to the location of instruction memory that holds the instruction, and it will increment the value of the current performance of the task by adding a value of 4. The second stage is its instruction decode stage, which consists of various modules. The first is instruction divide, which breaks the instructions in different stages such as opcode, opex, source, register, and destination, and immediate, and produces output. The OPEX and opcode are given as input to main control module, which generates various control signals for all the stages. Source and target register used to point at the location of register file. A 16-bit immediate offset is given to the sign extended block, which generates a 3 different 32-bit version of immediate offset. The third stage is execution stage, which generates branch address, data memory address, results, and write back address. The read address 1 from the previous stage fed to ALU. The ALU either generates a address of data memory or a normal result. ALU gives out branch result when comparison is done for branch output. It performs operations such as add, subtract, multiplication, comparison, and logical operations. The fourth stage is data memory stage. The read and write operators related to memory are controlled by memread mem and memwrite mem signal. The addresses from where data used to be read is given by the ALU, whereas the data to be written is provided by the previous read data to stage. The last stage is write back stage. This stage is smallest one, which gives the address of the register where data is to be written into R-type operands. And another important block is the hazard detection module. This module is basically to detect read after write data dependency and given to control signal, which are stall and instruction flash. The data dependency occurs when the read and write operation done in the same register. In this situation, this module pauses all pipeline stages and allows the write back stage to complete the operation. In these slides, I am showing the 5 stages of the Nios architecture pipeline, which are instruction fetch, instruction decode, execute stage, memory stage, and write back to the register stage. Nios architecture has 3 types of instruction set, which are I-type, R-type, and J-type. The Nios instruction types are almost similar as the MIPS instruction set architecture. The only difference is in the MIPS instruction set architecture, the opcode is in the MSB, whereas in Neost architecture it is in the LSB, and there is one addition which is in the OPEX. Neost architecture has 3 addressing modes, which are displacement modes, register mode, and immediate mode. The displacement mode has 2 more addressing modes, which are register indirect mode and absolute mode. In this section, we will discuss the development of Nios to design. We will first see what kind of basic elements we will need to construct each stage. After that, we will see the ways to handle hazards which arise due to pipeline without affecting correct operation and performance of the processor. There are several components used in the different stages of Nios to instruction architecture, and they are program counter, instruction register, register file, arithmetic and logic unit, and memory. Each of the modules are implemented in Verilog for the design. The benchmark program is shown in News2 format in this slide. Here we can see the R2 points to A vector and R3 points to B vector, and a dot product of the two vectors are placed in register R5 and stored in memory. In the right side column we can see the assembly language instruction representation in native News2 instruction format. But this sequence of code had data dependency and has to be improvised, and in my next slide I'm going to show that how can we improvise the nearest to instructions in order to avoid data dependencies. Here we can see we rearrange the instructions and write it in again in the rearranged way, and this way we can avoid the data dependency and we can also improve our performance. In order to ensure the entire design works perfectly, it is important to verify each module separately to ensure correct working of all its functionality before integrating all the modules. This is done by writing separate test benches for different stages of pipeline. After completion of above all the stages, we get a complete integrated design of our main module. This complete design is then tested using our program to ensure that it is working correctly. For this, we are going to use our test bench and we are going to test our main module in order to verify that our main the implemented module is working perfectly. Here we can see the dot product simulation result of our implemented Verilog code, and the expected result is 500 after putting all the values to check the functionality. And here we can see the final output comes after 71 clock cycle and it comes out as 500, which is our expected result, and we get the result in 71 cycle. Here we can see that the three stages pipeline of our final result output. In the third stage, which is the ALU stage, we get our final result and we pipeline the result in our memory stage, and from the memory stage we pipeline it in the write back stage, and finally we got our result. We can see the three stages of pipeline of our ALU output here. This slide we can see the simulation result of our factorial for our implemented Verilog code for the Nios 2 architecture set. Here we implemented the code for factorial 4, and we can see the result of factorial 4, which is 24 in the simulation result. The project can be enhanced to incorporate more complex operations such as cache memory can be also added to improvise the project. Forwarding unit can be done to add more performance in the design. Sign multiplication can be added for the next step in the project. The stall can also be reduced in the branching by moving back to the branch unit in the previous stage. One more idea is that even superscalar or super pipeline architecture can also be designed for further Neos 2 processor improvement. In this project, I have implemented the Neos 2 instruction set architecture in Verilog and simulated the waveforms and got my results or perfectly, and the design was implemented in 5 main modules: fetch, decode, execute, data memory, and write back stages. The whole design is pipelined into 5 stages so that each instruction is executed in each cycle. In the designing stage, the hazards like the structural hazards and the control hazards were taken care of, and due to data dependencies in the future instructions, stalling is introduced in the design. So here I am concluding my presentation. Thank you all for listening to me.